Welcome to Let's Get to the Marks, going through an A-level chemistry walkthrough question on aspirin and purifying all of that business. Let's get into it. What I suggest is you watch me go through the question and then you pause the video, have a go on a bit of paper with each section, and then unpause and watch the explanation. So the structure of 2-hydroxybenzene carboxylic acid is shown. Give the equation for the reaction of 2-hydroxybenzene carboxylic acid with methanol. In your equation, include the skeletal formula of the organic product. It's worth 2 fat marks. So let's get into it. Why don't you press pause, have a go at this one. Let's go. Okay, so we're going to zoom in a little bit closer like that, underline the key points. So we got our reactants, 2-hydroxybenzene carboxylic acid. It's reacting with methanol, so CH3OH. You can write that as displayed or however you want. And then they definitely want us to do the skeletal formula in this equation. So otherwise we're going to lose a mark and of the organic product. And I think we're going to need the side product as well because they want the full equation, but you get 1 mark for the full equation and 1 mark for the skeletal formula for the organic product. So this is my ester that is going to form. When you react this alcohol with this 2-hydroxybenzene carboxylic acid, the alcohol is going to react with the carboxylic acid. So it's esterification. We're going to have a condensation reaction where we've got addition and then the water is eliminated. So I've got my methyl group there. Don't forget my hydroxy group on the second. And then I'm probably going to have a water molecule, aren't I, coming off because I'm going to have lost the OH from the alcohol and an H from the carboxylic acid or the other way around. Don't forget it's skeletal. This will actually lose me a mark because look what I've done. Can you spot my mistake? I've left the CH3 right here. I need to get rid of that because this is skeletal formula. And so wherever there's carbon hydrogen, I just need to show a line. So the fact that I show a line after the oxygen means that that will be a methyl group. We assume that's a carbon with 3 hydrogens coming off. In fact, I might make that a diagonal line and there we go. That's the end of it. So let's move on. Brilliant. All we need to do is mark this up. So, oh, I forgot the side product. We've done the organic product and we're going to have H2O coming off as well. So let's give ourselves 2 marks, 1 for the equation and 1 for the skeletal formula for the organic product there. So 2 marks in total. Lovely jubbly. Okay, let me read this out for you. Aspirin is produced from 2-hydroxybenzene carboxylic acid by reactions with ethanoic acid in the presence of concentrated phosphoric acid. Add 2-hydroxybenzenoic, benzene carboxylic acid to a conical flask. Add excess ethanoic anhydride. Add a few drops of concentrated phosphoric acid. Heat the flask to 85 degrees for 10 minutes. Cool the flask and pour the contents into a 150 centimeter cube of cold water. Filter and wash the impure solid aspirin. Recrystallize the aspirin using a 50-50 mixture of water and ethanol. Check the purity of the aspirin. Aspirin can also be produced by reacting 2-hydroxybenzene carboxylic acid with ethanoyl chloride. State why ethanoic anhydride is preferred to ethanoyl chloride for this preparation. So ethanoyl chloride is like one of them ethanoic acid, essentially. Look, I'm drawing the structure for ethanoic acid, but instead of an OH group, we have a chlorine group there. Now, normally when you do a condensation reaction with ethanoic acid and an alcohol, you're going to release water. But this time, what are you going to release if you've got a Cl? Why don't you pause the video, have a go at this one? All right, I'm going to go over it. So you're going to release hydrogen chloride, and hydrogen chloride is toxic. So that's one of the downsides with ethanoyl chloride. Of course, the upside is that you generally wouldn't need the phosphoric acid catalyst. If you're using ethanoyl chloride, it's such a good reagent that you won't need a catalyst for it, whereas you do need a catalyst when you're using ethanoic anhydride. But the beauty of using ethanoic anhydride is your side product is ethanoic acid. So that's kind of cool. Ethanoic acid, basically a bit like vinegar, is not really going to be too dangerous like HCl, which would be dangerous. All right, and that's going to get you a mark. There might be some other reasons I can't think of right now, but you can check the mark scheme if you want. I'll put the link in the description. Let's zing down. We're going to hit 1.3. So 1.3. Let's zoom a little bit on this one. Oh, my phone's dinging. Give the name of the mechanism for the reaction of 2-hydroxybenzene carboxylic acid with ethanoic anhydride. It's worth 1 mark. And So when you do these esterification reactions, first of all, the alcohol or the carboxylic acid adds on, or the ethanoic anhydride as this, and then the side bit is eliminated because you end up with too many bonds. So something's got to give, and you draw that little curly arrow breaking off. So we call this addition elimination. Okay, so it involves both addition and elimination. Um, it's kind of like a substitution reaction in the end, really, but there we go. Right, 1.4 suggests the role of concentrated phosphoric acid. So that's going to be our catalyst. And as I said, if you're using a carboxylic acid for esterification, if you're doing acidic esterification, or you're going to need a catalyst. But if you use ethanoyl chloride, you don't. Right, suggest why reflux is not essential when the flask is heated to 85 for 10 minutes. And the reason for this is that the boiling points of the reagents and the products are above 88 degrees, 85 degrees, sorry. So yeah, the boiling point is above 85 degrees. I think aspirin's like 88, or it might be 90 degrees, but it's slightly above 85. So we don't need to worry about doing reflux for this. Okay, the next part, 1.6, complete and label the diagram to show how the impure solid is filtered. Now notice it says label and you got to complete. Now there are several things on the mark scheme that they insist on, but we're going to go through and bust this out. So what you're doing with impure solids, sorry, when you want to filter them with the old impure solid, what you want to do is connect a Buchner Hirsch funnel. And I used to just call it a Buchner funnel when I was at school, but you can show filter paper in the Buchner funnel. So it's a special type of funnel, a ceramic funnel with a long bit at the end. You can tuck that into a conical flask through a bung. That way it's like airtight. And you need to label the filter paper here. It's essential. It doesn't matter so much whether you use a dashed or a solid line. I've used a dashed line. I'm just used to doing that since my GCSE days, right? And then over here, you have a bung. That's not essential for you to label. I think you need to have it on the diagram to get the diagram mark, but you don't have to label that. And then you've got this empty tube. Well, you can connect a Bunsen burner tube to that, and then you connect it to a vacuum pump. And that's like a motorized pump that's going to draw the air out. And what that does is that lowers the pressure in the conical flask. So you have a pressure gradient from where your substance on the filter paper is to the lower pressure in the conical flask. So you're going to kind of suck. You're going to create a pressure gradient, and that's going to drain off all the liquid and filter that impure solid out. You're going to get all the solution come off and leave behind the solid. So it's just a sped up way of doing that. And you do need to label the filter paper and the vacuum pump. I forgot to put the word pump there. No, did he? But yeah, you need to label those two, and that's important. You don't need to explain that it's low pressure down there, and you don't need to label the Buchner Hirsch funnel. I would probably try and label it a Buchner funnel or just a funnel, but there you go. That's going to get you the 2 marks, one for the diagram, one for the correct two things labeled. Right, let's zing on. 1.7, suggest the identity of two impurities present in the filtered solid aspirin before it is washed in step 6 of the method. And this is worth 2 marks. Can you work out two impurities? If you go back and look at the stem, let's check out the stem of the question. We got 2-hydroxybenzene carboxylic acid. No, we're not reacting it with methanol. Let's go down to the method. Sorry, that was the previous bit. 2-hydroxybenzene carboxylic acid with ethanoic anhydride. So look, we've got our two reactants. Now the chances are that we're going to have at least one of those in excess, unless you've done it perfectly. And we've got our catalyst, which is going to be left unchanged. So impurities, you could go for phosphoric acid, you could go for ethanoic anhydride, or you could go for 2-hydroxybenzoic acid. So what are the other ones on the mark scheme here? Well, here I've got my 2-hydroxybenzoic acid thing, and that is going to react, right? I don't know where my OH from my carboxylic acid has gone, but never mind. That's going to react here with this. So I should have an OH there. Hold on. There we go. Now we got the OH. That's a little better. Right. Now what we're going to do, let me zing this over. That bit of my ethanoic anhydride is going to join on there with esterification. We're going to lose the side group. We're going to lose the hydrogen from the OH on the 2-hydroxy. And that hydrogen ion from the 2-hydroxy that was there is going to be here on its little lonesome. And of course, the lone pair on the oxygen is going to be attracted to that. And that is going to reform ethanoic acid as the side product. So instead of your normal esterification where you get H2O coming off, you're going to get ethanoic anhydride. So I was just pointing that out, that ethanoic anhydride, ethanoic acid, sorry, as the side product is also one of the things that could come off there. So we could have the ethanoic anhydride, the phosphoric acid, the catalyst, the 2-hydroxybenzene carboxylic acid, the other reagent, and we could have the side product, the ethanoic acid. Those are all possible impurities. Okay, zinging on to the last bit of the question, we've got describe the recrystallization process used to purify the aspirin, include the method and the apparatus used. Okay, I'm getting tired now. Just pause the video, have a go at this one on some scrap paper. Try and do 6 bullet points about how you recrystallize and purify the aspirin. Okay, so first step first, you've got to remember all of this. So put it on a revision card. It's a 6 bullet point one. Dissolve the aspirin in hot solvents. Use a minimum amount of hot solvent. Obviously, you increase the amount of solute that can be dissolved when you use a hot solvent. So when it cools, you're going to get the maximum amount of crystals coming out. So we want to use a hot solvent. So it's like totally saturated. When it cools, those crystals are going to come out. Filter it now to remove any insoluble impurities. So you now filter the solvent to remove those insoluble impurities. Then you cool it. So you filter it while it's hot. Then you cool it. And when you cool it, the crystals will all fully recrystallize out. Now we filter with the Buchner-Hirsch funnel and the vacuum pump, the thing we did the diagram of. We're going to filter that, and that's going to get rid of any of the solution. And then we're just going to be left now with our solid aspirin, and we want to wash that aspirin with cold solvent. So we're going to wash it with some cold solvent, and then we're going to dry it, and that's job done. Right, 1.9, final bit, state the physical property that is measured to check the purity of aspirin. Describe 2 ways the result could show that the product is impure. So pause the video, have a go. You know the coup. We do the melting point, and that's how we check for purity. And if something's pure, it will melt at an exact temperature. So, for example, if aspirin melts at 88 degrees, that's when it's going to melt. If it melts between 86 and 89 degrees, if it's still melting, some of it is still crystal solid at 86, 87, 88, 89, then it's melting over a range. And so that means it's impure. And the other factor, other than it should melt at an exact temperature, is that the melting point, that range will be lower. Hence why we add salt to the roads in winter to lower the melting point of water so that ice doesn't form. Don't forget, sharing's caring. Hit the like, punch up the bell, subscribe. I'll catch you lot on the next video. I'm out. Welcome to Let's Get to the Marks. Going through question 2 of the 2024 AQA Paper 3 Chemistry A-Level. The rate of reaction between calcium carbonate and hydrochloric acid is investigated using a continuous monitoring method. Place a conical flask on a balance and add approximately 20 grams of large marble chips. Add 50 centimeter cubed and 0.4 mole per decimeter hydrochloric acid. Place a loose cotton wool plug in the neck of the flask. Zero the mass reading on the balance. Start a timer. Record the loss in the mass MT every 30 seconds for 4 minutes. Wait for the reaction to finish and record the total mass loss, M total. Plot a graph of M total minus MT against time. Suggests why a loose cotton wool plug is placed in the neck of the flask instead of leaving the flask open or inserting a bung. So look, it's going to be my incredible level 9 art skills coming on show here. If you want to have a go at this, why don't you pause the video and have a go? So this is a common misconception here as to why we put cotton wool in the end of a conical flask. You should know the answer to this, as it's one they cover at GCSE as well. Essentially, this is a reaction between a carbonate and hydrochloric acid. So you're going to get carbon dioxide coming out. If you leave a bung in, it's going to build up and pop the cork or pop the bung or explode or whatever. You're going to get a pressure build up. So, and we also, the whole point of this reaction is to record the loss in mass. If you keep the carbon dioxide in, how are you going to do that? So the carbon dioxide can get through the small holes in the cotton wool so that it goes down as you want with the loss in mass of the carbon dioxide. As we'll see later on, that's proportional to the rate of reaction. So we can use that as a measure of the rate of reaction, the amount of carbon dioxide that is lost or the mass that is lost. Now the HCl is bubbling away in this reaction, and some of it might spit out if you left it open, and that would mess up your recording on the mass loss. So by having cotton wool in there, it catches any hydrochloric acid that is spitting out, and that liquid is caught on the cotton wool, and so will be measured when you the mass will be included on the scale, right? Because the cotton wool is part of the overall mass. So yes, that's one of the reasons why we have cotton wool instead of a bung to allow carbon dioxide to escape and to prevent hydrochloric acid from spitting out, which would produce the mass. Might be dangerous if you put your eyeball on the end of it, but yeah. Yeah, there we go. Right, let's go. I'm trying to arrange this so you can actually read it. Oh, this isn't going well. I'm knackered today. Cream crackered. 2.2, 20 grams of 20 grams of large marble chips is a large excess. So they use tons of calcium carbonate for just a small amount of acid. Suggests why they used a large excess of calcium carbonate. And why does this mean that the rate is only affected by the concentration of hydrochloric acid? So what is the purpose of them using a large amount of calcium carbonate? Pause the video and have a think. Okay, it basically nullifies the effects of surface area by having a large amount of calcium carbonate. You've got a huge surface area in contact with the acid, and it means the surface area is constant. It never becomes a limiting factor. It never becomes something that changes the rate of reaction. And this means that only the fact that the hydrochloric acid reactant is decreasing, and therefore the rate of reaction, we can see from the curve on the graph, the rate of reaction is starting to go down towards the end there because the reactant's getting used up. Yeah, so it basically keeps the surface area constant. 2.3, the mass of carbon dioxide produced in time t is equal to m. The total mass of CO2 produced is m total. Explain why m total minus mt is proportional to the concentration of hydrochloric acid remaining in the flask at time t. So essentially you've got this reaction going on with calcium carbonate, and hydrochloric acid is going to produce calcium chloride plus water, right? Plus carbon dioxide, balance it up, put a little 2 in front of the HCl, and then we got a ratio of 2:1 with carbon dioxide. Now, don't let that fool you. It is still proportional, right? If I double the amount of hydrochloric acid, I double the amount of CO2 produced. So we know that the amount of CO2 lost is proportional to the amount of HCl that has reacted. So M total, which is the total amount of CO2 produced, minus MT is going to be equal to however much unreacted hydrochloric acid is left in the flask. And it's all because the amount of carbon dioxide lost is proportional to the rate of reaction, or is proportional to the amount of HCl used up, reacted. So at any one time, the total carbon dioxide lost minus the MT at that time is going to give us, which is going to give us minus the loss in mass of the CO2 at that particular time, is going to give us the amount of HCl left. So at M total, all the HCl's been used up. Yeah, you get the idea. All right, I'm going to stop waffling. Let's go through the answers here. So M total minus MT is proportional to the concentration of... Oh, God, I've got to plot this graph. All right, I'm just going to put this data on. Okay, so there we go. I've roughly put all the crosses on. You can see I've labeled the axes. I've put the data on. It all looks a bit jiggledy-joggledy, but you can see I've fit it on. You need to go over 50% of the graph needs to be used. So you can see when I draw this line, we've used over 50% of the vertical portion and 50% of the horizontal. So you're going to get the marks for that, and also correctly labeled the axes with the units. And you're allowed to be like a half little square out on these plots. So don't worry, that one is slightly out. How do I get rid of that cross? Okay, let me delete that. That cross should be closer to the line. It should be 2 little squares down. There we go. Anyway, you can check. Yeah, you're not here for the how to plot a graph. So there we go. Now, the questions we've got following up on this is state how, if you look at 2.5, which is under the data table on the left-hand side, state how the graph in figure 2 confirms the rate of reaction for this reaction. Rate equals K bracket HCl. And so... yeah, how do we know the rate equation is rate constant times the concentration of HCl? Well, looking at this graph, it is a constant gradient. So wherever I go on that pink line and work out the gradient, it will be the same between any 2 points on that pink line. Also, the straight line of this graph, if we extend it, it would go through the origin. So it's a straight line through the origin, or you could just say the gradient is constant. And that's what that rate equation shows. It's that it's proportional. In this experiment, the variable measured is mass loss. What are two other ways you could measure? So you did this in GCSE. So the volume of CO2 released, we could collect with a gas syringe, or we could do the change in pH because we've got HCl, and obviously it ends up being pH 7 once you've only got the once all the carbonate, once you've just got salt, carbon dioxide, and water, obviously salt and water left, you're going to have like a pH of 7. So you're going to have a pH that's increasing. You could use a pH meter, and you could use that as an indication as the rate of reaction, or I guess temperature if it's exothermic or endothermic. All right, welcome to Let's Get to the Marks. I'm going through an Arrhenius equation for A-level chemistry. So what I suggest you do is you have a read of this question, press pause on the video, have a go at answering these parts to the question, and then unpause and watch my explanation. Right, I'm going to go through it now. So the thermal decomposition of but3N1O is investigated at different temperatures. Here's but3N1O. You can see it's breaking down to form an aldehyde, it looks like, and an alkene. The results from this investigation are used to calculate the rate constant K at each temperature. So we've got 553, 563, 573, 583, 593. Table 2 shows some results. Complete table 2 with the missing values at 573. Now what to do here, really simple. Look, here's the temperature. This is 1 over the temperature. So you're just going to do 1 divided by the temperature. And if you want to check that, when you feel like baffed in an exam, you're like, oh my God, like, how do I do the missing values? Well, look, all the values are complete here. So you just try it out. Here you go, 1 divided by 563, and you should get 1.78 times 10 to the minus 3. So here we're going to do 1 over 573, and that's going to give us like 1.7. It's like 1.74, but you round it up to 1.75 times 10 to the minus 3. I think it's 1.745. So you're going to round up to 1.75 times 10 to the minus 3. We want to keep the same amount of digits, keep it uniform with the rest of the results in here. So the same amount of significant figures, etc. So there we go, 1.75 times 10 to the minus 3. Now for this one, we want to do ln K. Well, we just got to do ln in the old calculator. The brackets are going to pop up on your calculator. Then put in 15.6 times 10 to the minus 4. And if you're in doubt and thinking, oh, is that definitely what I do? Well, just do ln times 8.4 times 10 to the minus 4, and you're going to get minus 7.08. So you'll know it's the correct way to do it. And that is going to give you minus 6.46, roughly, and that is going to give you the first mark on the board for this question. There we go. Now, the overall order of reaction can be deduced from a piece of information in one of the column headings. Identify the piece of information and deduce the overall order. So when we look around here, what will give us the order of the reaction? It's actually this s to the minus 1, the fact that K is s to the minus 1. So K is s to the minus 1, K is the rate constant. And now if it was s to the minus 2, it would be second order, but s to the minus 1, it is first order. And that's going to score us 2 marks. And we got a mark for that. So there's 3 marks altogether there. All right. Now we've completed the table. Let's get on to the Arrhenius bit of the, oh my gosh, I keep putting ticks on. Let's get on with the question, basically. So here you can see we've got the Arrhenius equation can be written in the form shown. Ln K equals ln A minus EA over RT. On the grid, figure 3, plot a graph of ln K against 1 over T, and that is worth 2 fat marks. What we're going to do now, we're going to, on the grid, figure 3, plot a graph of ln K against 1 over T. So we've got our table here with all the data, and we just need to plot it on here. And then what we also need to do is calculate the activation energy using the gradient of the graph. 3.4, so we want to do 3.3 to plot the graph, and then we want to use our graph, once we've done it, to calculate the EA in kilojoule per mole for the thermal decomposition of but3N1O. Gas constant is 8.31 joules Kelvin. So we want to be careful here. This is in joules, and our final answer needs to be in kilojoules, so we're going to have to do a conversion when we get to the final answer. But you're going to use your gradient to do that. So, and that's going to get you loads of fat points. This is a really common question with the Arrhenius equation where you have to know that the gradient on this 1 over T um, natural log, whatever it is, K, ln K graph, this 1 over T ln K graph, you need to basically know that that is equal to minus EA over R, and then you can rearrange that and find the activation energy. And that's what we're going to do now. So let's get into it. All right, so first off, I've got to plot my points. So I'm going with the 5.30. We're going to put our points all on here. And if you plot these up, you can smash these on, and then you want some sort of line of best fit. Now, you're going to need to calculate the gradient. I'm just doing the whole thing, but it's probably not as accurate, but I'm being lazy. So I'm going to get 2 marks for the plots and for the line of best fit. So 1 mark for the plots really and 1 for the line of best fit. So that gives me 2 lovely marks. Now I want to calculate the gradient in my effort to work out the activation energy. Now I'm doing the gradient of the whole thing, which is a little bit but there we go. So what is the gradient? X over Y? No. It's Y over X, isn't it? Yeah. So right. Gradient is Y over X. Need to know that. So let's work out, and also the gradient is equal to the minus the activation energy over R. Once we know the gradient, we can then times by R to leave us with the activation energy. So let's do that. And this is a really common thing, so you've got to know. So if I want to work out X, I'm essentially going to do 1.82 times 10 to the minus 3, and I'm going to minus that from the other side, which is 1.68 times 10 to the minus 3. Now, I'm not saying this is the most accurate way to do it. You might want to do it, you might want to make your calculation of the gradient a little bit smaller and do it from the first plot to the last plot. I've extended the line and doing the extended line. So I'm probably going to get some inaccuracy here and not exactly match the Markscheme answer, which is probably not very good. Right. So I'm going to get 0.00014, and that is my X. Now I need to work out Y, and Y, I'm starting up here at minus 5. Is that minus 5.10? No. That's minus 5.05. Sorry, minus 5.05. What we're going to do is find out where my line ends at like 7.90. So I'm going to go Y is equal to 7.90 minus like 5.05. Now I don't need to stick the minuses in my calculator and go, oh, do 2 minuses make a plus? Remember, what I didn't write is when you're doing the gradient, you're looking at the change in Y. So the difference between the start and the end of Y over the difference between the start and the end of X. So you're looking at the change in. So the change here is going to be 2.85. Now, as I say, if I did this somewhere else on my line, and my line of best fit might not be that accurate, just look how it's come off the point there. If I do that somewhere else on the line, between 2 points on my line, I could pick another 2 points, a smaller one, and I'll probably get this much more accurate and much more, much closer to the actual result in the Markscheme. I'm just showing you the way that I'm doing it. So Y is equal to 2.85. Now I'm going to divide this by 0.0014 or 0.00014, and that is going to give me 20,357. Now, when I say that mine is on the limit of the accuracy, if you check the Markscheme answer is 1900, 990 or something like that. But it does range up to 20,400. So my answer would be valid and would be within the range accepted by the Markscheme. Okay. It's just that I've extended my gradient, I've extended my line of best fit, and I've done the gradient from there. It would be more accurate for me to say go between 2 points like here and here, work out the gradient there, or actually more accurate to do this first point and this last point. That will probably bring me closer to that 19,900, the answer in the Markscheme. Okay, right. What do we do now? So we've worked out the gradient. In my gradient was 20,357. I know that looks a bit dodgy, but there we go. What I want to do next, let's make that 0 and that's 7 better. Right, 20,357 is going to be equal to minus EA, minus the activation energy, divided by R. Now, what I'm going to do is R is 8.31. I'm just going to multiply 20,357 by 8.31. So, and that is going to give me the activation energy more or less, which is 169,166.67. What we do have to remember is that R is in joules. So our activation energy at this stage is in joules, but activation energy is always represented in kilojoules per mole. So what we need to do is convert joules into kilojoules, and we do that by dividing by 1,000. So activation energy is in kilojoules, so we're going to divide by 1,000. And generally, activation energy, you think is the minimum energy required to break bonds in the reaction to get the reaction started. So it's generally going to be endothermic with a positive sign. So I'm not so bothered about whether my answer comes out with a negative sign. I'm going to flip it and make it a positive sign. I'm not even going to put a sign. I'm just going to write the answer as 169, and we're going to round that to what, 0.2 kilojoule per mole. So divide that by 1,000, and that's what I would do to the -1. There we go. 169.2 kilojoule, sorry, per mole. And that's going to be my answer. Okay. Now the textbook answer I think is 165 kilojoule per mole, but that's if you came up with the 1900 and whatever, 19,000 for your gradient. But you do that by doing a more accurate gradient, but I was lazy. I just did the whole thing. Anyway, hope that helps. Let's move on. All right, going on to the final part of the question, 3.5. 2-mether-pent-4-N2-ol decomposes in a similar way to but3-N1-ol to produce an alkene and carbonyl compound. Deduce the structures. Well, let's bust up here and let's have a little look. Look, we had but3-N1-ol, and it says this second reaction breaks down by thermal decomposition in the same way. This snapped into an alkene. Look, goes CH2, CH, CH2, CH2, CH, CH3. So it's kind of snapped there, and it's left behind what's that? Methanol. So we've got an aldehyde and an alkene being formed. So what they're saying to us is break this bad boy. Whoa, gone too far. No, did he? Right, break this bad boy into an alkene and an aldehyde, and you could yeah, and then why don't you pause the video and have a go? Okay, so you can see what I've done here. I've drawn out the displayed formula for this. So we got the double bond, we got that going on there. We've got the two CH3 groups coming off of this carbon, and then we've got the OH also coming off of that carbon. And so if we want to split this into an alkene and an aldehyde, I guess the most obvious place to split this is going to be here. We're going to split along there. So we're going to make our alkene is going to be CH2. Oh, we're going to put the double bond. Oh my gosh, that's so ugly. Right, CH, and then we can't leave it at CH2. We need to attach a hydrogen there. There's going to be an H there. So CH3. Otherwise, we're going to leave it with only, we're going to basically make a carbocation if we don't add a hydrogen on there. So there's our alkene. Now I just need to piece this together to make an aldehyde. And this just looks like it's going to be CH. Right, so we're going to kind of have like CH and then CH3, and we're going to have two lots of those still hanging on there. The only difference here is we're going to have that is going to be there, and we're going to have an H there. So yeah, that was kind of ugly, wasn't it? Right, so I kind of want to draw the structural formula for this. So we're going to have that. No, that's got 5 bonds. How else can we have that? We're going to have a ketone. Okay. So we're just going to go CH. No, we're not going to have CH. Get rid of the H, you donut. So I guess like that. But that doesn't look right, does it? So notice I had to draw out the display formula to make sure, because otherwise I might have sort of thought, oh, it's going to form an aldehyde like the other one, and then done that, and then ended up with 5 bonds around there. So that's, you can see it's a ketone. Now, is that the best way to write the formula? I don't know. It should be accepted. There's nothing wrong with that, but you might be better off going CH3 to CO like that, and then keeping the carbonyl group together, the C and the O. All right, guess we could go CH3COCH3 like that. That would also be acceptable. And there we go. Anywho, that's going to get us holiday marks. Nice. Don't forget sharing is caring. Hit the like, punch up the bell, subscribe. I'll catch you lot on the next video. Okay, going through an A-level acid and base chemistry question walkthrough. Don't forget to pause the video at the start of each question, have a go, and then unpause and watch the explanation. Figure 4 shows how the pH changes at 0.1 mole per decimeter. Sodium hydroxide solution is added to 25 centimeter cubed to 0.08 mole per decimeter aqueous propanoic acid. State the meaning of weak in this context of propanoic acid is a weak acid. Why don't you pause and write it down? All right, I'm going to go through the answer. So a weak acid is an acid that partially dissociates, you can say partially ionizes, when in aqueous solution, which is equivalent to saying when dissolved in water. So when it dissolves in water, it partially ionizes. So the propanoic acid becomes propanoate ions and hydrogen ions. You know the equation with the reversible symbol, folks. All right, let's move on to 4.2. So what we're looking at now is suggest why a student doing an experiment to produce the curve that was shown here in figure 4 would add the sodium hydroxide solution dropwise at the equivalence point. The equivalence point is the bit where you can see that straight line in the middle of the graph. So kind of between pH 6 and 11 there. So why is it they slowed down the volume of sodium hydroxide and only added it drop by drop instead of centimeter by centimeter? They started adding like millimeter cube by millimeter cube, drop by drop. Why did they do that here? You can see that just a small change, just 1 centimeter cube difference in the sodium hydroxide can cause a change of like 3 pH levels. So we just need to put that down. Close to the equivalent point, a small change in the volume of sodium hydroxide equals a large change in the pH. Therefore, if you add it too quickly and you're not adding it dropwise, you might actually miss the equivalence point. You might go past and not find out where your neutralization has occurred. Okay, that's going to give us 1 mark there as well. Don't forget to hit the like. Massive help to me on the channel if you hit the like. I'm here to do hundreds and hundreds of chemistry A-level walkthrough questions to help you pass your exam. So if you could hit the like, it would be a massive help. Right, 4.3. Give an expression for Ka for propanoic acid CH3CH2COOH. Use this expression to show that pH equals pKa when half the propanoic acid has reacted with the sodium hydroxide. Now, pause the video, have a go at this on paper. This is purely theoretical, no maths needed. Okay, think about the dissociation equation. So we've got our propanoic acid, reversible symbol, goes to propanoate ions and hydrogen ions. You know that the expression for Ka, Kc, Kw, whatever you want to do, is always products over reactants. So we just want to put the products, which is going to be the ethanoate ions multiplied by the hydrogen ions. Just get the formula right for propanoate, CH3CH2COO minus, and then H plus. By the way, you can't put H plus squared here. That's simplifying the expression. They don't want that. So you will lose the mark if you put H plus squared at the top there, even though it's relevant. They don't want it. Okay, so 1 mark for the Ka expression. Now we know that if you have 10 molecules of propanoic acid, breaks down to form 10 molecules of propanoate ions. So we know that the propanoate and the propanoic acid is going to be equivalent. This means they cancel out, which means when we cancel them out of our expression, Ka is equal to the hydrogen ion concentration. Now, as the pKa is the minus log of the Ka and the pH is the minus log of the H plus ion concentration, then that tells us that pH must be equal to pKa because Ka is equal to H plus, so pKa must be equal to pH. Okay, so when half the propanoic acid has reacted, then we know that our propanoate ions are going to be equal to our propanoic acid ions because we're going to have like sodium propanoate if it's sodium hydroxide we're adding, and we're going to have an equal amount of sodium propanoate as we do to propanoic acid at the point where half has reacted. All right, let's zing on. 4.4, use the pH from figure 4 when half of the propanoic acid is reacted to calculate Ka at 298K. It's worth 2 marks. Now, we've just gone over this, that the Ka, and we've just proved that the Ka is equal to the hydrogen ion concentration when half of the propanoic acid has reacted. So We just need to calculate the Ka. So we need to calculate the hydrogen ion concentration. So let's find out when would half, it's obviously fully reacted at 20 centimeters because it's been neutralized. So when is it half of the acids reacted? Well, that's at 10 centimeters of sodium hydroxide, right? So when we've added 10 centimeters of sodium hydroxide, half the volume of the equivalence point, we know that it has neutralized. Oh, sorry. We know that half has been added there. What is the pH? pH is 4.5 roughly to 4.6. I think they'll give you a range in the mark scheme here because it's in between a big square. Each little square is 0.4, and so in between one of those big squares is either 0.5 or 0.6. So we're looking at 4.5, the pH. Now you know the relationship between pH. It's the minus log of the hydrogen ion concentration. So we just need to reverse that. And so we're going to put, generally on most scientific calculators, you're going to press shift, get the little box in the corner, 10 to the box in the corner, then you're going to put minus 4.5 in there. So we know that we're going to go minus 4.5, and that is going to give us the hydrogen ion concentration. And the hydrogen ion concentration is going to be equivalent to the Ka, and then you need to put it to 2dP, or A level is best to go 3 significant figures. So as we know, when half of your propanoic acid is left, we can cancel out the propanoic acid and the propanoate ions because they cancel each other out in our Ka expression. And that's because you're going to have equal amount of propanoate ions will have reacted with the sodium to form sodium propanoate. So you're going to know you have the same amount of propanoate ions roughly as propanoic acid. So we cancel those out. So Ka equals the hydrogen ion concentration. So we're going to do shift minus 4.5, which is the pH when half the propanoic acid was used. And that is going to give us the hydrogen ion concentration, which is like 3.163 if we round up. Yeah, not really. 3.1623 is a better answer, I think. I don't think 3.163 is a good answer, but times 10 to the minus 5, and that would get you the marks. I'd probably change that, guys, and leave it as either 3.16. I'd leave it as 3.16, to be honest, times 10 to the minus 5, 3 significant figures. You don't need to go more than that. Otherwise, you get yourself in trouble like me there. 4.5, when sodium hydroxide solution is added to aqueous propanoic acid, the solution formed acts as a buffer when between 5 and 15 centimeters have been added. Explain why the pH stays approximately constant during this experiment. So why don't you pause the video, grab your pen. It's theoretical. 2 sentences will get you this. Okay, so I'm going to go through the explanation. Buffers are basically solutions that resist the change in their pH when a small amount of acid or alkali has been added. I haven't worded that very well, but you see what I mean. Okay, when you add a small amount of acid or alkali, their pH will remain constant. Why is that? Well, that is down to our dissociation equation. We can use that if we want. We could write the one with sodium hydroxide and the sodium propanoate ions, but that's long. So I'm just going to write propanoic acid breaks down, once again, just to show you, into propanoate ions and hydrogen ions. Remember, we've also got loads of sodium propanoate as well because we've reacted sodium hydroxide. We don't have a lot of propanoate ions from this expression, but we're going to have sodium hydroxide plus propanoic acid make sodium propanoate and water as well. So we're going to have loads of sodium propanoate ions as well, which will absorb the addition of an acid. But we're talking about, as the sodium hydroxide is added, why does it change very little the pH? And it's because it's acting as a buffer. And this means that any hydroxide ions that are added, because we're adding sodium hydroxide, are absorbed by the hydrogen ions. They react with the hydrogen ions. And therefore, those sodium hydroxide ions react with the hydrogen ions to form water. They remove the hydrogen ions. Now, what do we know from Le Chatelier's? If you lower the concentration on the right-hand side, the left-hand side is going to dissociate more in order to oppose that change and release more hydrogen ions. So essentially, we lower the amount of hydrogen ions because they react with the hydroxide ions. Now, that would change the pH, wouldn't it? You'd have less hydrogen ions, so your pH would go higher, become more alkaline. However, our propanoic acid, this is the buffer part of the propanoic acid, therefore shifts to the right, its equilibrium position, and it dissociates to release more hydrogen ions to oppose the change. And so you actually get relatively little change in the hydrogen ion concentration and therefore the pH. Now, the reverse of this question, so that's going to get you all of the marks, just basically saying hydrogen ion concentration goes down as it reacts with hydroxide ions, so more propanoic acid dissociates, or the equilibrium position shifts to the right, releasing more hydrogen ions. However, I just want to go through, imagine they said, how would it resist the change if you added an acid? We can't really show that here because I haven't written the equation, but sodium hydroxide would react with propanoic acid and fully react to create lots and lots of propanoate ions, right? Which would sodium propanoate fully dissociates in solution. So you actually have loads of propanoate ions as well, which will mop up any acid you add and do the reverse of this situation and shift the equilibrium in the reverse. Right, the next question, methyl orange and universal indicator are rubbish. They're not suitable for titration or for this particular titration. Explain why. So when we look at methyl orange, what we're going to do here is see that the equivalence point here is between about 6 and what, pH 12? No, 6 and 11. I guess the straight part of the graph is roughly maybe 7, pH 7 to 11 is the straight part of this graph. What we need to do is find out, does methyl orange change between pH 7 and say 10? If it does, it will be perfect for this titration. But we can assume, I know you might say, how am I supposed to remember it off by heart? We can assume it doesn't. Look, I'm going to Google, not equivalence point, you buck. I'm going to Google what's the pH range of methyl orange. Let's check it out. AI will help us here, peeps. Methyl orange is an acid-base indicator with a pH range of 3.1 to 4.1, changing from red in acidic conditions below 3.1 to yellow in basic conditions above 4.4. So, wrong paper. There we go. Back to where we are. Okay, so we can tell here that the range of pH, the change in the color of methyl orange, does not fall or match the equivalence point for this reaction. Therefore, methyl orange is not suitable. Methyl orange changes color between 3.1 and 4.4. However, the pH, the equivalent point here falls between like pH 7 and 11 or 6 and 11, something like that. So basically, I think you could just assume if it's not suitable, you would just say, hey, methyl orange does not change color at the equivalence point, or it doesn't change its range where it changes color doesn't match the equivalence point, and you could just put that without knowing the exact pH range for methyl orange. And you'll probably get asked about phenolphthalein as well. Right, universal indicators rubbish for any titration regardless of the pH curve, and it's because universal indicator has a gradual change in color, no definite change in color at a specific pH. So it goes like from green to blue, so it's very subjective as to whether it's changed color. There's no clear definite change. Don't forget sharing's caring. Hit the like, punch up the bell, subscribe. So let's get into this one. Some complexes containing transition metal ions are colored. Explain why some complexes containing transition metal ions are colored. List the factors that affect the color. Describe how colorimetry can be used to determine the concentration of a colored complex. This is worth 6 marks. So grab a pen, grab some scrap paper. And what I want you to do is have a go at this first. Time yourself. You can set a timer on your mobile phone or whatever. Give yourself about 6 minutes, 7, 8 minutes to do this. And it's roughly going to be kind of 2 marks a section. They put it into 3 sections for you, and that's how the mark scheme works. It's based on 3 sections, basically. And if you want to get all 6 marks, you've got to pretty much in the entirety, about 3/4 of the information needed for each of those 3 sections, which I'm going to go through now. So why don't you pause the video, have a go, and then unpause and watch me go through the walkthrough. Okay, so let's answer the first section. Explain why some complexes containing transition metal ions are colored. So what I'm going to do is use an example here to explain this to you, and then I'll put what I put for my answer. I'll tell you what would be in my answer for this first section. But I'm just showing you this is a nickel ion without ligands or ligands, however you want to say it, right? So we just need to put the electrons into the box orbitals, and we need 6 electrons in its 3D because it ends with 3d6. So I'm going to fill out each one with 1, and then that first 3D orbital, I'm going to put the extra one in. We've got a bit of spin pairing going on there, and that is without ligands. Now, when you get a ligand like H2O, remember ligands are a species that can donate its electrons to the central metal ion, so it has like a lone pair of electrons that it can donate, often like water. Water's got 2 lone pairs, but we're going to get 6 water molecules around this nickel. Anywho, when ligands surround the nickel, the 3D orbitals split. And what do I mean by that? Well, they're all on the same energy level at first, and then they split so that a couple of the orbitals gain an excited state or a higher state, and then 3 of them are in their original state called the ground state. And so we can just split those orbitals. I've put 2 with the single electrons up and 4 of the electrons in 3 of the 3D orbitals down. They're in the ground state. So we've got 2 different energy levels. Now what happens? So that is just our complex when there's no light. If you were in a dark room, that is the complex, what would be going on, and it's the electron situation. Now we're going to shine some visible or white light, and you have to be very explicit about that. You cannot just say light on the mark scheme. You must say visible or white light, meaning the light that comes from the sun or from a light bulb, a normal light bulb, and you shine that onto the complex. And what happens is that provides some energy for one of the electrons to be excited, or more than one electron to be excited, and they leave the ground state. As you can see here, I've circled in green. That little spin paired electron has jumped up to the higher state. So what we're going to get the marks for this first section is for saying 3d orbital split with ligands, visible light or white light is absorbed, causing electrons to move from the ground state to the higher state. Now, depending on the gap of energy there, how much energy is actually absorbed to move the electron up, all waves, whether it's light, water, whatever, all wave or sound, all waves can be absorbed, transmitted, or reflected. Now, the amount of light that is bounced off, reflected, or goes through, they come together to form something called a color complement, and that's the light we see. So if this electron I've got in my example absorbed red light from the white light, then it would reflect blue and green, and that would be the color that we would see, reflect or transmit, i.e. go through it. And so we call that the color complement. Any light, any wavelength of light that is reflected, or frequency, you can say, of light that is reflected or transmitted, forms a complement, meaning both the transmitted and reflected join together to make the color. So I guess green and red would make a kind of brown color if they're reflected, and blue was absorbed. Okay, so anyway, let's move on. That's the first stage covered, and I've underlined the points in green that are essentially the mark scheme points of my explanation. So the next one is list the factors that affect the color, and the factors that affect the color are the type of ligands, the coordination number, the type of metal, and the oxidation state of the metal ion. So if it's iron or copper, that makes a difference, and then if it's +1, +2, +3, that makes a difference. And then the coordination number, which is the number of bonds formed with the ligands, and then the number of ligands, which isn't the same always as the coordination number. Anywho, let's move on. Okay, so moving on to stage 3, describe how colorimetry can be used to determine the concentration of a color complex. So we just basically want to use some of the key points about colorimetry. So if you had an unknown concentration of, say, a copper complex ion, right, you would take the exact same complex ion solution where you know 5 concentrations. So take 5 known concentrations, measure the absorbance at each concentration, and plot a calibration curve. So you get a curve of 5 known concentrations like 10%, 20%, 30%, 40%, 50%, whatever. And you measure the absorbance at each percentage. You plot that on a line graph and you'll get something called a calibration curve. Now take your unknown copper complex ion solution, right? Take your unknown, use your colorimeter to shine light at it and measure the absorbance. And now you can plot the absorbance onto your curve and draw a line across from the absorbance of your unknown. Where it meets the line, draw it down to the concentration, and booyah, you're going to find the concentration of your unknown solution. And I'll sketch that out in a little diagram for you here so you know what I'm on about. So you can see I'm not very good at drawing these graphs. I've put the concentration at the bottom as 0, 1, 2, 3, 4, 5, whatever. That's not going to be a concentration. I guess that could be percentage, 1%, 2%, 3%, 4%, 5%. That would be a bit dumb. So it could be like 0.1 mol, whatever. 5 different concentrations. I can't be bothered. And then up the side, we got the absorption, and you're going to plot 5 on. That was a bit of a crusty graph. Okay. You'd probably spread them out a bit more, but yeah, then you just draw the line across. If my unknown was 30% absorbance, I'd draw it across and look, it's 3.1 concentration. So there you go. That's how you find the unknown on a calibration curve. Right, we're zinging on. Oh, we're zinging on. 5.2, figure 5 shows the visible spectrum of CuH2O62+. We got the absorbance here. We got the wavelength on the x-axis that is absorbed. Use the wavelength at the peak of the curve in figure 5 to calculate the change in energy in joules of an electron when it absorbs radiation with this wavelength. The Planck constant H equals 6.63 times 10 to the minus 34 joules per second. We've got, not per second, joules second. Speed of light C equals 3 times 10 to the 8 ms to the -1. So you've got to know this equation off by heart. If you don't know this equation, you might be kind of stuffed. But essentially, energy gap is equal to hv, or we can say the energy gap is equal to hc over the wavelength, and we use our little wavelength symbol there. It looks actually like a wave going in the water, the wavelength symbol. Okay, let's solve this. So V equals the light absorbed, H equals the Planck constant, 6.63 times 10 to the -4. C is the speed of light, 3 times 10 to the -8. 3 times 10 to the 8, not to the -8. Whoopsie. And then we have that little wave symbol is for wavelength. Now, what do we want to do? Well, essentially, we can say the energy gap is equal to hc over the wavelength, because yeah, you can just remember it as that. Delta E equals hc over the wavelength. So we know that the use the wavelength at the peak of the curve. So I've drawn a line here going to the peak, right? And at the peak of the curve, we didn't actually need the absorbance. The wavelength is 800 nanometers. So I know that energy gap is equal to 6.63 times 10 to the -34. That's H. That's the Planck constant, times the speed of light, which is 3 times 10 to the 8 meters per second. And I'm going to divide that by 800 nanometers, which is the wavelength. However, wavelength is not supposed to be in nanometers. You have to remember this. So this is another tricky part to it. Wavelength is actually in meters. So we need to convert the 800 into meters. Now, how are we going to do that? We're going to times by 1 times. No. We're going back up. So we divide. Always remember, when you go up the units, you divide, which is kind of counterintuitive. So we're going to times 1. We're going to divide by 1 times 10 to the 6. Divide by a million. So it's going to be 0.0008 meters. That's going to be the wavelength. So we're going to do 1.989 times 10 to the -25. How did I get 1.989 times 10 to the -25? I times h by c, so Planck's constant by the speed of light. And then we're going to divide that by the wavelength in meters, which is going to be 0.0008. And that is going to give me 2.48625 times 10 to the -22. We're going 3 sig fig because we're at A level, so we're going to put that, as that 6 is bigger than 4, we're going to put it to 2.49 times 10 to the -22 joules, and that's going to get us all of the marks for that one. And that's the end of the question. Don't forget, sharing's caring. Hit the like, punch up the bell, subscribe. I'll catch you lot on the next video. Let's smash those chemistry A-level exams. Okay, welcome to Let's Get to the Marks, going through the 2024 Paper 3 A-Level Chemistry AQA MCQ section. Let's go. It's going to be great. It's going to be great. Nobody does a walkthrough like me. Okay, yeah, enough of the crap impressions. Let's get on. Let's have a go at this one. Why don't you pause the video, have a go at this one, and then unpause and watch the explanation. Which row contains 2 species with different numbers of electrons? So we've got to work out the number of electrons in each of the 2 species in each question and see if which one has a different number in each species. What do we mean by species? Well, like ammonia and hydrogen fluoride, different chemical compounds. So we've got 7 electrons in nitrogen, 1 in each hydrogen, that's 10. And then hydrogen fluoride, well, the atomic number of hydrogens 1 and 9 for fluorine. So there's 10 electrons in each. That's not correct. Now let's look at the carbonate ion and the nitrate ion. So for the carbonate ion, we have, what is the atomic number of carbon? It's 6. So we have 6 electrons in carbon and we have 8 in oxygen. So we want to do 3 8s, so 24 electrons, plus the 6 is 30. But check out the little -2 thing, right? There's a little -2 here, but a carbonate ion, that means it's carrying 2 extra electrons. So we mustn't forget to add 2 electrons. So we have 32 electrons in the carbonate ion. Lovely bubbly, if my maths is correct. I think it is. And then we're going to do the nitrate ion. The nitrate ion is nitrogen, which has an atomic number of 7, so that's 7 electrons. And then we have the 3 times 8 again for the 3 oxygens is 24. 7 plus 24 is 31 electrons, right? Yes, that's right. Now notice we've still got the negative charge on the nitrate ion. That's an extra electron. So rather than taking away an electron, you've got to add an electron when you see those minus signs. So they've both got 32. They don't have a different number of electrons in each species. Now let's look at this. We've got this H3O plus ion and 3 electrons in the 3 hydrogens, 8 in the oxygen, but it's got a plus charge. So we want to, this time, there's an extra positive charge, so one electron is missing, so there's only 10 electrons in that. Let's check out HF2 plus. So HF2 plus is 2 9s are 18 for the fluorine, and one for the hydrogen is 19, but it's got a plus charge, so it's got 18 overall. So yeah, that's definitely the right answer, because one of them's got like 10 electrons, one's got like 18 electrons. So yeah. Let's just check this last one out to make sure. Methane is 4 for carbon. 7 for nitrogen. Hold on, that doesn't make sense. This is going to be different as well. What have I done wrong? Carbon's in group 6. I was thinking of the outer shell of carbon. So carbon has 6 electrons, plus 4 for the hydrogen, 10 electrons. The nitrogen has 7, plus 2 for the 2 hydrogens is 9 electrons, but it's a minus charge. So altogether 10 electrons. So that one doesn't have a different number of electrons. And here we go. Okay, let's zoom into this next MCQ. Which element has the highest third ionization energy? Why don't you pause the video, see if you can work it out, draw out the structures, and see if you can work it out. All right, I'm going to go through the answer. So here we go. So lithium has an atomic number of 3, meaning 3 electrons. So we're 1s2, 2s2. I'm going to show the box orbitals because we're going to need to explain that. If you think about it slightly, we're taking the third electron. So really, we're going to remove that 2s1 and that 1s2 one, and then we're going to be left with just 1 before the nucleus. So pretty close to the nucleus, but no shielding. So going to be pretty high for lithium. Look at beryllium. With beryllium, we're breaking into a brand new energy level. So I reckon beryllium's is going to be even higher than lithium's, because you're removing those first 2 electrons from the 2s2, which will be quite difficult because that is a full orbital, but then you're breaking into a brand new energy level. Now let's look at potassium. Potassium has 19 electrons, so we're going to go right up to 3s2, 3p, and we have 6. So the first ionization energy, 4s, sorry, 1, there we go, 19 electrons. We're going to remove one of those, and we're going to remove 2, well, we're going to remove one of the 3 P's, and then we're going to have to remove this one circled in red. But this is a partially filled 3P subshell, right? So at the end of the day, it's a partially filled subshell, so it's going to be easier to remove than breaking into beryllium, which is a whole new energy level in a filled subshell. Calcium, let's check out the old calciomy. Calcium is going to be 4s2. So 3p6, 4s2. So we're going to remove both the 4s electrons. Now I'm trying to bus into another completely filled energy level, brand new energy level, and a totally filled subshell. So it's really between beryllium and we're looking at calcium. They're going to be the ones that have the highest third ionization energy. So if we look up at lithium, that's definitely not. That's going to be a relatively easy one to remove because it's a partially filled shell. Yeah, it's going to be difficult. It's close to the nucleus, but really beryllium's higher because we're looking at a full brand new energy level. We're breaking into the first quantum level, and it's a filled subshell. Again, for potassium, the third electron we're removing is from a partially filled subshell, a 3p5. And a calcium, we are breaking into a 3p6. So, and there is shielding. Right, there's no shielding for beryllium, so beryllium is going to be the hardest one to remove because it feels that nuclear attraction the most. It's very close to the nucleus. There's no shielding blocking it from the nucleus. Whereas, although the third electron in calcium is also in a totally filled subshell, so hard to break into, it is shielded from the nuclear attraction, so should be a lower ionization, third ionization energy than the one for beryllium. And there you go. Okay, this MCQ question is on yield. Compound P is converted into compound R by a 2-stage synthesis via compound Q. The yields for the individual steps are P to Q, and that is a 50% yield. And Q to R is only a 30% yield. What is the overall yield of R in this synthesis? Well, think about it. We're going to lose 50% of the product or only get 50% of the product with Q. So we're going to go 100 times 0.5, 50%, and then times 0.3, which is times by 30%. So our answer is 15%. Easy peasy lemon squeezy. You know what? That was so quick. Let's do another. This one is on the formula of ammonium ethandioate. Okay, so what we need to break down here is, do you remember the formula of ammonium? Hopefully you do. Ammonium is NH4 plus. Don't get it mixed up with ammonia, which is NH3. So the ammonium is an ion, the ammonium ion, NH4 plus. And then we have the ethandioate ion, which is C2O4 2 minus, or minus 2. So all we have to do is balance the charges here to get the formula for the compound. And we need 2 ammonias to go with 1 ethandioate. So the answer's B. And there we go. Okay, this A-level MCQ question is about dative covalent bonding. So question 10, which diagram shows the formation of a dative covalent bond? Why don't you pause the video, have a go with a pen and paper, and then I'll go through the explanation. All right, here we go. Okay, guys, this first answer, A, check out which way the arrow's going. So you've got ammonia. Ammonia does form ammonium with a dative covalent bond. However, in the ammonium ion, the lone pair of electrons must come from the nitrogen to the hydrogen. The hydrogen ion doesn't have any electrons to donate to the nitrogen, so the arrow can't possibly go that way. That's wrong. Over here, very similar, we've got boron trifluoride. Boron's in group 3. How many electrons does it have? 3. So it's given those all to the fluorines, the 3 fluorines it's bonded to. So it doesn't have any electrons left over. There's no lone pair that it can donate to the nitrogen there. On the ammonia. In fact, the arrow would go the other way. The arrow would go from the nitrogen to the boron trifluoride because it would be the lone pair of the nitrogen. So that one is wrong. Now let's look here at H3O plus, and we can see that water, hopefully you know, oxygen's in group 6, 2 of its bonds, 2 of its electrons are there, so it does have a lone pair. It's got 2 lone pairs actually, so it can donate one of those lone pairs to a hydrogen ion, so that is a dative covalent bond. So our answer is going to be C. And if we look at the bottom one, we can see what the issue is here. The silver ion does not have the electrons to donate to these 2 ammonia molecules. In fact, it would be the other way around. It would be the lone pairs from the ammonia molecule that would form a dative covalent bond with the silver ion. It wouldn't be the other way around. So the arrows, once again, are in the wrong direction on D. So where are we? All right, question 11. Which substance does not have bond angles of 120 degrees? So if you're looking at 120 degrees, you're looking at your kind of trigonal planar situation. So let's check out benzene. By the way, pause the video, have a go at this one, and then unpause and watch the explanation. So is it A? Well, no. A, you can see here, benzene has 1 hydrogen coming off a carbon, and then you've got the other 2 bonds to the other carbon. So that's 3 bonds around the central atom, the carbon at each point of the benzene. So it's 120 degrees, so that's not our answer. We're looking for one without 120 degrees. Now, boron is a group 3 element, 3 electrons in the outer shell. It's bonded to 3 fluorines in boron trifluoride. Therefore, it's going to be 120 degrees as well. There's no lone pair of electrons around there. So you're looking at 6 electrons, 3 pairs. So let's look at cyclohexane. So cyclohexane is not benzene. It doesn't have that delocalized pi orbitals. So each carbon in cyclohexane has 4 bonds. So generally, we can suspect when you have 4 pairs of electrons, you're looking at 109.5. So that isn't 120 degrees. So that's probably going to be our answer. Why have I put a cross through it? Well, I'm an idiot. Let's look at graphite. You can see graphite, each carbon's bonded to 3 others. So that's 120 degrees. Yeah, so the answer is going to be cyclohexane. Let's get rid of that cross there, guys. And that's going to be tetrahedral if the shape. So probably 109.5 would be my guess. It might be slightly different to that, but there we go. Bosh! Why don't you pause the video, have a go, unpause and watch the explanation. So here we go. Which molecule does not have a permanent dipole? So if we look first of all at ammonia here, we've got the nitrogen with a lone pair, and I think you all can work out what the shape of this is. It's going to be pyramidal, and it's definitely not symmetrical. Now, these hydrogens and this nitrogen, there's a difference in the electronegativity. Nitrogen is one of the most electronegative in the periodic table. So that's going to be delta negative, that's going to be delta positive, and there is definitely going to be a positive side and a negative side. There's going to be a permanent dipole in this molecule. So
this one definitely does have a permanent dipole. So we get rid of that. Now, if I replace this phosphorus trichloride, essentially phosphorus is also in group 5. So all I've got to do here is change this around a bit. However, the chlorines are more electronegative this time. So with phosphorus trichloride, same sort of situation. We've got a group 5 element with a lone pair there, and it's bonded to 3 there. So it's going to be pyramidal again in its shape. So it's not a symmetrical molecule, and this is going to be dealt a positive in each of these bonds compared to that because the chlorine is more negative than the phosphorus atom. There's going to be a permanent dipole because they don't cancel each other out. So let's get rid of that. Now, if we look at what have we got here, we got like sulfur dichloride, kind of sulfur's in group 6 like water, right? So it's going to have 2 lone pairs and it's going to bond to these chlorines. And I think you remember what the shape of water is. It's going to be what, 104.5. It's a bent non-linear molecule. And this means although this is delta positive and these are delta negative, as these are more electron withdrawing than the sulfur atom, that is going to be a permanent dipole because it is not a symmetrical, fully symmetrical molecule. They don't cancel each other out because of its bent shape. If it was linear, they'd cancel out. So let's say we had magnesium chloride, then this would not have a permanent dipole because these would be cancelled out. However, this is not a linear molecule, it's a bent molecule, so they don't cancel out. Now we're going to check out the final one in our little permanent dipole question. And the final one is the silicon, whatever this is. What is this? Tetrachloride? Who knows? Um, yeah, it's going to have that old tetrahedral structure, 109.5. And guess what? Individually, the chlorine and the silicon is a polar bond. But because it is a symmetrical molecule, all of these dipoles cancel each other out, and this is a non-polar molecule. So our answer is going to be D. So there's a difference when we're talking about a permanent dipole in a molecule and when we're talking about an individual polar bond. So if they say the word polar bond, then you want to look at individual bonds. And yes, silicon, whatever this is, tetrachloride has polar bonds, but it doesn't have a permanent dipole. It is a non-polar molecule, and it's because all of the bonds are equal distance apart and they all cancel each other out. The dipoles cancel.
This one's on hydrogen bondings. Which compound forms the greatest number of hydrogen bonds per molecule in the liquid state? Why don't you pause the video, have a go at the question. I'm going to whip through the answers. All right, here we go. Right, this first one, A, is propanoic acid. So let's just draw roughly out the formula. Okay, so of course, to get hydrogen bonding, you need to have an oxygen atom attached to a hydrogen. So we've got some hydrogen bonding going on there. It can bond to another carboxylic acid group, another propanoic acid. But the beauty of the carboxylic acids is they also get some hydrogen bonding forming between the oxygen on the carbonyl group of 1 and the hydrogen on the alcohol part of another carboxylic acid. So there we go. I'm not going to draw the full thing out, just going to put R there, but there should be a carboxylic there as well. So you can see there's a hydrogen bond, and then the hydrogen on the alcohol bit can form a hydrogen bond to the OH on another carboxylic acid. So in their liquid state, you're going to have loads. They have 2 hydrogen bonds per molecule forming. Okay, so they can form 2 H bonds per molecule. Now, if we look over here, this is a ketone. What's this? Propanone. So if we think about it, propanone can't do hydrogen bonding because there's no O attached to an H. There's no N attached to an H or no fluoride attached to an H. So there's no hydrogen bonding whatsoever. You're going to get dipole-dipole forces in propanone in the liquid form. Now we've got propanal. And propanal, once again, no hydrogen bonding. There's a hydrogen and an oxygen close to each other, but they're not bonded together, so they won't do hydrogen bonding. Again, this will have some sort of dipole forces in the liquid state, but it's not as strong as hydrogen bonding, so we can say A is the best answer so far. Now, this one will have hydrogen bonding. This is propanol, so they're all propans, these. And you will get hydrogen bonding, but of course, if you just have propanol molecules, you're only going to get one hydrogen bond formed between each 2 alcohol molecules, right? So this can chain onto another hydrogen, another propanol, and that can go on to another, etc., like that. So essentially, there's only one hydrogen bond formed per molecule kind of thing.
So there's only one point of hydrogen bonding here. So this is going to have a lower melting point and therefore weaker hydrogen bonds. Don't forget sharing's caring. Hit the like, punch up the bell, subscribe. Let's get to the marks.
Okay, looking at question 14, the Maxwell-Boltzmann distribution curve is shown for a gaseous reaction mixture. You could say gaseous or gaseous, however you like to say it. I like gaseous. Number of molecules with given energy on the left or the y-axis, and on the x-axis we have energy. What is represented by the total area under the curve? Well, it's not going to be A, the total energy of molecules in the reaction mixture, but remember, the height of the curve at any one point gives us the energy, right, of the molecules. So that's the line itself. The area under the curve is the number of molecules. Now, is it the number of molecules in the reaction, the total energy? No, again, it's not the energy. It's not A or B. They're both talking about energy. So we want to get down to C and D, which is really looking at the total number of molecules. Is it the number of molecules in the reaction mixture, or is it the total number of reacting molecules? No, it's C. It's the number of molecules in the reaction mixture in total. They're not all reacting, are they? In a reaction mixture, they're not all reacting at the same time. It's only the ones which are past this line, the activation energy line, that have enough energy for successful collisions. So there's only ever a proportion of those reactants reacting. Okay, bosh.
Okay, guys, we got another A-level multiple choice question. Let's go. Question 15, or whatever. A student investigated the reaction between magnesium and hydrochloric acid. We got a little equation here. We got a ratio of magnesium to hydrochloric acid is 1 to 2. Is that relevant? I don't know, but I just get into a good habit of writing down my ratio when I see a question, just in case that comes up. The results are plotted on this graph. We've got the volume of gas over here. We've got the time in seconds. Which value is closest to the rate of reaction in centimeter cube per second at 70 seconds? We actually don't need that ratio. Anywho, you might think you've got to do this. So let's go along. It says, excuse me, which value is closest to the rate of reaction at 70? So you might go, well, let's go along to 70 seconds at the bottom and draw a line up. Draw a line across. Look at that bent line, right? 62.5, and then we're going to do centimeter cubed divided by seconds to get cm s to the minus 1, cm cubed s to the minus 1. So we might go for 0.9, and I think, don't beat yourself up, right? Don't slap yourself in the face if you got this, because that's quite standard for us to think that that is the answer, but it's not. This is the wrong answer. So how do we find the right answer? Well, let's check out that line on our gradient there. We're going to try and find the gradient on a curved line. So we need to find the gradient there at 70. How are we going to do that? We're going to draw a tangent. Now, mine might not be very accurate because I'm doing this on the PC. Excuses, excuses. But when you draw this line, try and make the space either side of the dot that you've drawn at 70 seconds. Try and make that equal. Now, is that equal? That is not equal. Okay, that's a well warped. So you kind of trying to make it so that the gap between the curve and the line that you draw, the tangent that you draw, is roughly equal. I reckon that's good enough. I'm going with this. I know it's not perfect at all. I know I'm not going to get a perfect answer, but these answers aren't close together. I should be all right. Okay, and now what we want to do is work out the change in y and divide that by the change in x, just like you would for a gradient. And that's going to give me roughly close to one of these answers. Let's see, what's that, 34? I think y is 34 to 80, my change. So changing y over changing x. And what is my x? My x, I think, is starting at 0, and then it goes to just before 110, 108. Maybe it's 109, I don't know. It might be 109 or 110. Okay, does it really matter? I don't know. So we've got, essentially, we have 80 minus 34. What is that going to give us? 46? Oh my gosh, my maths is so bad. 46 over 108, I think. And if we smash that in the calculator, what will that give us? There you go. And I got roughly 0.4259 centimeter cubed per second. Roughly. Again, it's not exact science here. And look, when you compare that, you can see, look, it's closest to 0.4. You might get a slightly different answer because your tangent might be a lot better than mine, but there you go. It's obviously closer to that answer. So don't fall for the old 0.91. And don't forget, sharing's caring. Hit the like, punch up the bell, subscribe. Let's get to the marks. Statement explains why the rate of reaction increases when a catalyst is added at a constant temperature. So we've got to remember our Maxwell-Boltzmann's distribution curve. So we've got the number of particles shown underneath the line, and then we've got our activation energy, and then when you add a catalyst, does the curve change or does the activation energy change? Hopefully you know a catalyst lowers the activation energy, so we're going to put a dotted line here, and we can call this EAC, energy of activation with a catalyst, or AEC, whatever. That is the activation energy. So A, the collision frequency increases because there is a decrease. The second part to that sentence correct. There is a decrease in the activation energy. We can show that there. How? So we'll leave a question mark there. But the first part, collision frequency increases. Does it? Collision frequency increases because there is an increase in the activate. Well, there's not an increase in activation energy. We definitely get rid of that. And then we've got the proportion of successful collisions increase because there is a decrease in activation energy. And that's going to be our correct answer, because what you've done by moving that line back, you've increased the number of particles that can successfully react. You haven't increased the number of collisions. To increase the number of collisions, you'd have to increase the temperature, and we haven't increased the temperature here. So C is our correct answer. D, proportion of successful collisions increases because there is an increase. Again, it's talking about an increase in the activation energy. That would make less particles react. So yeah, D is incorrect, and the correct answer is C. So there's just a greater proportion shown by this orange circle of particles that can now react. You haven't changed the frequency of the collisions or the strength of those collisions. You've just lowered the threshold for a successful reaction. You've lowered the energy needed. Now we're going to go on to a slightly more advanced multiple choice question, number 17 here. Just going to zoom in on this. A cell with an EMF of plus 2.15 volts is made from two electrodes. The half equations for the two electrodes are shown. We've got the positive electrode. What do we call a positive electrode? Anyway, we've got, okay, so an EMF 215 made of two electrodes. We've got a positive electrode, negative electrode. Now, this always is a bit confusing for me, but the positive electrode, your electrode with a more positive cell potential is going to go on the right hand side, and on the left hand side is going to be your more negative electrode potential. And what we're going to do the right hand side, EMF is equal to the right hand side minus the left hand side. In this case, we can say that EMF is equal to the cathode, the E cathode minus the E anode. And yeah, that's the equation we need to use to solve this. Now, I always get myself jumbled up with these ones, but basically you've got the EMF is going to be equal to the E cathode minus the E anode. Basically, what would go on the right-hand side of your electrochemical cell minus the left-hand side, which is normally the more negative electrode potential, the one that's releasing electrons or being oxidized, is normally on the left. So we're kind of doing reduced minus oxidized. Yeah, you could call it reduced minus oxidized, or right-hand side minus left-hand side. Now, because I've written a minus 0.46, that's basically like plus 0.46. So what I want to do is I want to get rid of that, and it's a minus 0.46. So I'm going to add 0.46 to each side to get rid of the minus 0.46. And so I'm going to add minus 0.46 to each side, and that is going to get rid of the 0.46. Now you might say, why am I adding a minus 0.46 to each side? Well, I'm trying to get rid of the minus 0.46, and two minuses make a plus. So by adding minus 0.46, I'm going to make 0 on the right hand side of this equation, and that's going to leave me, I have to do to both. So I'm going to add minus 0.46 to the 2.15, and that is going to give me 1.69. Now, an alternative method, folks, alternative method is just to do 2.15 equals right-hand side minus 0.46, and then just plug each one of these answers in and see which one equals 2.15. So start with the minus 2.61 instead of RHS, and then go to minus 1.69, and you'll find the only one that gives you 2.15 is if you put plus 1.69 minus 0.46, and there you go. Values of the ionic product of water, Kw, at different temperatures are given. Kw equals 6.40 times 10 to the minus 15 mol 2 dm minus 6 at 18 degrees. However, at 25 degrees, we have Kw equals 1 times 10 to the minus 14 mol 2 dm minus 6. Which statement is correct for 1 mark? The concentration of hydroxide ions in water at 18 degrees is 8 times 10 to the minus 8. The dissociation of water into ions is an exothermic process. The pH of water is the same at 25 and at 18. Water becomes less acidic as the temperature is raised. So why don't you press pause on the video, have a think about it, see if you can select the right answer and justify it, and then watch the explanation. All right, I'm going to go through the explanation for this. So what we've got to bear in mind is that Kw is equal to the hydrogen ion concentration times the hydroxide ion concentration. And also that when water dissociates, as some of these are about the dissociation of water, reversible process, but water dissociates into hydroxonium or hydronium ions, H plus we can say, and OH minus, hydroxide ions. And that's an endothermic process, so that requires energy in, whereas the formation of water is exothermic and requires energy out. Right, now you've got those details, you might want to have a go and see if you can work out the answer. Anywho, I'm going to go through it. So as the hydrogen ions must equal the hydroxide ions, right? For every water molecule that breaks down, you're going to get one hydrogen ion or hydronium ion, whatever you want to say, and hydroxide ions. So the concentrations are going to be equal. So if I want to find H plus or OH minus, I've just got to do the square root of the Kw. So I'm going to square root 6.4 times 10 to the minus 15, and guess what we get? We get 8 times 10 to the minus 8. So it's absolutely true for A that the concentration of hydroxide ions in water at 18 degrees is 8 times 10 to the minus 8. That's the correct answer. Now, I want to go through the others just to over-explain things. So the dissociation of water into ions is an exothermic. Well, we can see no, it's endothermic when it dissociates into hydrogen ions and hydroxide ions. That's wrong. The pH of water is the same at 25 and 18, right? We can prove this is not true and that pH is temperature dependent. So what we can do, remember I said the hydroxide ions are equal to the H plus, so I just need to square root these to find the hydrogen ions, right? So if I square root 1 times 10 to the minus 14, then, sorry, I put minus 4, I meant minus 14. 1 times 10 to the minus 14, you're going to get 1 times 10 to the minus 7. And if you minus log 1 times 10 to the minus 7, you're going to get 7. So minus log is doing the working out the pH, so you're going to find that the pH is 7. So the pH of water at 25 degrees, this is why we tend to say pH of water is 7, but it's actually only 7 at 25 degrees. If we change the temperature, as we're going to see now, let's do the one at 6.4 times 10 to the minus 15. So we know that hydrogen ion and hydroxide ion concentration are equal. So if we go to temperature 18 degrees, where the hydroxide ion concentration was 8 times 10 to the minus 8, then the hydroxide ion concentration and the hydrogen ion concentration are both 8 times 10 to the minus 8. So we can just do minus log 8 times 10 to the minus 8, smash that in the calc. So let's minus log, this is the hydrogen ion concentration, which is equal to the hydroxide ion. And you're going to get like pH 7.09. So it's not the same. Look, it's pH 7 over here, and it's pH 7.09 over there. So we can see that the pH has increased at lower temperatures. Actually, the pH has become more acidic at higher temperatures. So as temperature increases, what does Le Chatelier say? He says that it's going to favor the endothermic side, and the endothermic side is the forward reaction, and that's going to increase the number of hydrogen ions and therefore increase the concentration, which makes sense because pH 7 is a higher hydrogen ion concentration than pH 7.09, and pH 7 is at 25 and 7.09 is at 18. Okay, enough of my whiffle waffle waffle. Let's go on to question 19. Consider the periodic elements from sodium to chlorine. Which statement is correct? So from sodium to chlorine, does sodium have the smallest atomic radius, aluminium highest melting point, sulfur is the most electronegative, or chlorine has the highest ionization energy? Pause, have a go. Okay, I'm going to go through the explanation. So if you, whatever. So let's look at what's next to sodium in the periodic table is magnesium, right? The proton number has increased. However, the electrons are being added to the same shell. I would expect the atomic radius to decrease, would be the general trend, right, going across. So sodium can't have the smallest atomic radius because magnesium has more protons, therefore a stronger electrostatic force of attraction between the nucleus and the outer electrons, and the outer electrons are being added to the same shell, more or less, aren't they? So there we go. Aluminium has the highest melting point. Oh, this is a tricky one. Aluminium definitely has a higher melting point than sodium and magnesium because it's got a 3+ charge. The metallic positive ions have a 3+ charge, and the delocalized electron, and there'll be 3 delocalized electrons for each aluminium 3+. So there'll be a stronger force of electrostatic attraction between the highly charged aluminium positive ions and the 3 delocalized electrons with each ion. So I would say that aluminium definitely has a higher melting point than the first two in the period, sodium and magnesium, but we'd have to look at the other elements in the period 3. Anyhow, we'll come back to that. We'll put a question mark there. Okay, silicon. Yeah, I'm a little bit worried about silicon. When we think about aluminium, we've got to think the next one in line after aluminium is silicon. Silicon's in the same group, group 4, as carbon. So it's just after aluminium, and it's in the same column in the periodic table as carbon. And carbon's giant covalent, and silicon used in silicon chips and everything is giant covalent. So it's a case of, does giant covalent have a higher melting point than giant metallic? And I think giant covalent does. It's only giant ionic that beats giant covalent in melting point terms. Right, sulfur's not more electronegative than chlorine. You go further to the right, the more electronegative you get, and chlorine has the highest first ionization energy. So it's either B or D here, peoples. Yeah, well, chlorine, we just talked about the atomic radius. So chlorine must have a smaller atomic radius than all of the elements before it, as electrons are being added roughly to the same energy level, the third energy level. And that means the shielding is roughly going to be the same, but it is going to have a greater nuclear charge, 17 protons. So it's got a 17 plus charge, attracting those outer electrons in. Yeah, we're going with chlorine as the highest first ionization energy. Aluminium is not as high melting point as a giant covalent, which is silicon. Of course, aluminium would have a higher melting point than the other covalent substances, so the group 6 and 7 substances, because they're just simple covalent. All right, guys. Right, we're going on to question 20 here. Which statement correctly describes a trend down group 7 from Cl to I? Okay, the boiling point of HX increases. Oh, that's pretty easy, right? That's the X is a halide, so it could be HCl, HBr, HI, HF, whatever whatever astatine is, AT, isn't it? Yeah, so they basically get bigger, don't they? And so the hydrogen halides get bigger. So Van der Waals forces or London forces, whatever you want to call them, are going to increase with the size of the electron cloud. So yeah, A is the true one there. We don't need to worry about any of the others. Obviously, bond dissociation energy decreases, doesn't increase. Right, 21. Which statement about chloride ions is correct? They are oxidized by concentrated sulfuric acid. No, it's an acid-base reaction. You need to know this one off by heart, actually, that one for A. That's part of your knowing about the reducing power of the halide ions. So here's a chance to revise it. It's going to be NaCl plus H2SO4. Now, it could use potassium chloride. It could be any form of chloride ions. And that's going to make sodium hydrogen sulfate and hydrogen chloride. And we're going to see that the sulfur is +6 here and +6 in the sulfuric acid. So there's been no oxidation or reduction, no gaining of electrons. It's not a redox reaction. Does chloride ions form a cream precipitate with silver nitrate? No, cream is bromide. Silver AgBr is cream, isn't it? AgI is yellow and AgCl is white, so it should be white. So that's wrong, that one. Does it form a cobalt-2 complex with a tetrahedral shape? Well, I'll put a question mark there. We'll think about that in a minute. Does it have an electronic configuration of that? No, that's 16 electrons. Chloride ions have 18 because chlorine has 17 electrons. When it's an ion, it has 18. So it's going to be the tetrahedral shape. And chloride ions, as a ligand, they are bigger than H2O. So you don't get 6 of them around there because of their size. You can fit 4 around a central metal ion, and so they're going to form a tetrahedral shape. Aqueous aluminium sulfate is added to aqueous sodium carbonate. What are the formulas of the precipitate and the gas formed? This is just one of those, you've got to know with your complex ions, all the substitution kind of reactions. So you've got to know those off by heart. So it's going to be either one of these two, and you don't get sulfur dioxide given off. So it's this bottom one, D. You just need to learn these off by heart. I suggest making revision cards of all the ones on your spec. What is the correct structural formula for 4-chloro-2-methypent-2-enoic acid? So what we want to do here is draw the displayed formula of this out, and then from that, convert it into the structural and then try to match it up with either A, B, C, or D. Why don't you scribble out the displayed formula on a bit of paper, have a go, pause the video and do that, and then see if you can match it up to the right one. All right, let's go. All right, let's go through this. So what I'm doing here, I'm numbering it with the carboxylic acid being the high priority
in this molecule. So that is going to be carbon 1. Carbon 2's got a methyl group coming off of it, and the double bond. Carbon 3 doesn't have anything coming off of it, although I've done 5 bonds. What a wally. So we're going to go through and we're going to convert this CH3, and then it's going to be CHCl, and then CH scribble, because I had to scribble that out, because you can count round each carbon should only have 4 bonds. Now I'm going to have a double bond. So I'm going to lick a double bond in here with the CH, and then we're going to go CH again, because you've got that C carbon 2 as 1 hydrogen coming off it, then bracket CH3, and then COOH. I don't know why I've got a little line. Oh no, that's the number 1. Okay, so it's C. That's the one it matches up with. There we go. Wunderbar. 24. In which conversion does a nucleophile attack the organic reactant? I'm getting tired now, so I'm going to try and speed through. You've got the cyanide here. You should know that the nitrile, the CN minus with a lone pair, that is going to be your nucleophile. It loves positive things. And of course, we've got an aldehyde over there. We've got propanol. It's going to attack that lone pair there is going to, that should be a curly arrow, but that's going to attack that delta positive carbon on the aldehyde group. Right, 25. Compound Y has the structural formula. Which compound is a position isomer of Y? Oh, this one's a difficult one. Position isomer, you just generally move one of the kind of functional groups. So, you know, they might be saying like if we need to move the kind of ester link there, because we've got that COO, that ester link. So what the hell is that? 1, 2, 3. Yeah. So you kind of got like ethanoate. What is that? Methyl propyl, 2-methyl propyl ethanoate kind of thing. And where are we going to do? We could move that methyl group there, and that would make butyl ethanoate. If we move that methyl group over there, that would be a positional isomer. That would make butyl ethanoate. This one's a little bit difficult because on the Markscheme, they want you to move the methyl group over here and make it propyl propanoate. But in my view, there's no reason why butyl ethanoate isn't a positional isomer of that. I know that's an isobutyl group with the CH3 and the 3 carbons next to it, but still, yeah. The most popular answer then, unconfident one, is propyl propanoate. Which compound shows EZ isomerism? I'm not going to go through all of these. As I said, I'm starting to wear out here. So what you would do is I'll show you how to do it. The correct answer is D, and I'll show you why, and you can just apply that, sit there and draw out A, B, and C, and that will help you see why they're not the same. So if you put the double bond there, it's pent 2-ene. So first of all, pent, draw your 5 carbons. On the second carbon, whoops, numbering it the wrong way, the double bond is the most important high priority thing here, so we want to give it the lowest number there, 2. So we've got pent 2-ene. Now it's 3-methyl, so I'm drawing my methyl group coming off of there. Then over here, I've got kind of an ethyl group. Now, that looks a bit rugged. Let me simplify it for you up here by folding everything around. So we've got our methyl group off the 3rd carbon there. Then we've got the ethyl, CH3, CH2. Then we got the hydrogen coming off here, and then the methyl group, carbon 1, coming off the bottom there. So you can see that does EZ isomerism. Why? Because each carbon atom on the double bond has different groups attached. Hydrogen, methyl, and then the second carbon has a methyl and an ethyl. If you do the others, you'll find they don't fit that. What is the product when 3-methyl-butan-2-one reacts with acidified KCN? So let's have a little look here. What we want to do when 3-methyl-butan-2-one underlined reacts with acidified KCN. Now, acidified means we've got hydrogen ions. So whenever they say acidified, you've got hydrogen ions knocking about. Now, if it was HCN, you wouldn't need to acidify it, but HCN is very dangerous, so it's better to use KCN. Okay, let's check it out. Check it out. So we have butan-2-one. So I want my my ketone group on the 2nd carbon, and then that means my methyl group is going to be on the 3rd carbon, and that's going to be delta positive, and the oxygen delta negative. Of course, my nitrile, I'm going to do it attacking from the top. It's a lot easier. Let me rub out that one at the bottom. My CN with a lone pair and the minus is going to attack that delta positive carbon. What's going to then happen to the oxygen? The oxygen is going to have to lose one of its bonds. So the lone pair is going to go to the oxygen, make it negative. And then that hydrogen from the acidified KCN is going to get attacked by the lone pair on the oxygen. And you're going to get like a 2-hydroxynitrile, right? Well, you're going to get a hydroxynitrile formed. And in this case, it's going to be 2-hydroxy because the nitrile group is going to be attached to the 2nd carbon. And the, anyway, the nitrile now takes priority. I'm waffling. I'm waffling. You can see the nitrile on what was our second carbon. The nitrile will now take priority over the hydroxyl group. So we're going to number this with the nitrile as carbon 1. And so we need to number this up, right? Let's scribble that out. Well, hold on, let me get the old black out because this pink is hard to see, and I'll show you this. So CN is higher priority than OH. You can find anywhere. If you Google, AI will give you the list of all the order of all the functional groups. You just get to know them. So CN is going to be number 1. Is carbon 1, then we've got carbon 2, then carbon 3, then carbon 4, and then we've got 2 methyl groups. We've got 1 coming off of carbon 2. So first of all, the main chain is butanitrile. Then we've got a methyl group coming off of carbon 2 and another methyl group coming off of carbon 3. So we're going to have 2, 3, di meaning 2, methyl butanitrile. So I'm going to circle in green. You've got a methyl group there attached to the second carbon, a methyl group there attached to the third carbon. Then I've got a hydroxy group attached to the second carbon. So we're going to be 2 hydroxy, 2, 3, dimethyl butanitrile, and that is going to be answer A. Oh my god, I've spelt that wrong. I can't move it around. You get the idea, right? 2 hydroxy, 2, 3 dimethyl butanitrile. That is answer A. Okay, don't forget to smash the like if you're enjoying the video. It massively helps me out. You Marty Tuckers. This is another one which is just pure memory recall, so I'm just going to tell you the answer. Which statement concerning nylon 6,6 is correct? Nylon 6,6 can be hydrolyzed by aqueous sodium hydroxide. You just got to know that off by heart. Okay, it's a condensation polymer, so easy peasy pudding and pie. Which statement about the industrial production of ethanol from ethene at 300 degrees is correct? So the use of an acid catalyst increases the yield of ethanol. Remember, acids do not affect the yield. They just speed up the time it takes to get to equilibrium. The reaction is slower than fermentation. No, fermentation is done at 30 degrees. This one's circled up there, 300 degrees. It's going to be a lot slower fermentation. An increase in temperature at constant pressure increases the value of Kp. Now, Kp and Kc, these constants, are not affected by pressure or concentration. They're only affected by changes in temperature. So an increase in, because of the ratio with the concentration and the pressure, an increase in pressure at constant temperature, so we're left with D, increases the equilibrium yield of ethanol. Well, what do we know? Le Chatelier says if you increase the pressure, the equilibrium will shift to the side with the least gas molecules. So that's going to be the right-hand side, which is the side with the ethanol. So yes, increasing the pressure is going to increase the yield of ethanol. Look, 2 gas molecules to 1 on the right-hand side. So when you increase the pressure, it's going to do the opposite by Le Chatelier's principle. It's going to shift to the right, the equilibrium position, and we're going to get a higher yield of ethanol. Wunderbar. All right, we're going to move on. As I said, guys, it massively helps me out if you hit the like. It encourages me to make more videos and increase my turnover of A-level chemistry videos. Right, 30. Which compound is formed by acid hydrolysis of phenol benzene carboxylate? Ooh, well, you should know that a phenol basically is when phenol, which is an OH attached to a benzene ring, is a side group. So if it's a side group, the phenol, it means the hydrogen's been removed. So phenyl here is our, or when we have a benzene ring as a side group, it's phenyl. But we're going to have our carboxylic acid and our phenol, and they've lost water in a condensation reaction, and they've basically formed that ester link. And so we have benzene carboxylic acid has become benzene carboxylate, and the phenyl is the one on the left there. Okay, so if we do hydrolysis, we add water back, we're going to get a carboxylic acid. Oh my gosh, that's level 2 GCSE art. That's supposed to be a COOH group there. And then you're going to have the phenol reformed, right? You're going to have the benzene ring with the OH reformed if you do hydrolysis. So one of the products is going to be D, C6H5COOH. That's the benzene carboxylic acid. Now, you wouldn't get the top one there because that's got a CH2 group attached to the alcohol. It would just be C6H5OH, which is phenol. Which type of polymer is the most difficult to hydrolyze? It's going to be a polyalkene. All of the others, polyamides, polyesters, and proteins, they are formed during condensation reactions. They're condensation polymers that water has been removed. So they can easily be hydrolyzed by adding water back. In which polymer does hydrogen bonding occur between the polymer chains? Well, not the polyalkene. There's no dipoles there. You're going to get hydrogen bonding with the polyamide because you've got nitrogen, you've got oxygen, you've got hydrogen all getting together to make hydrogen bonding. Okay. Let's zing down. 33. Which structure shows a zwitterion of an amino acid? Now, zwitterions have a neutral charge. So the zwitterion has a positive and negative bit, but they cancel each other out. So check this one out. This got 2 minus and a plus, overall plus. That's got 1 plus, 2 minus. Overall, it's a minus charge. That's gone. That's just got a minus charge, so that's gone. This one's got 1 minus, 1 plus, cancels out to 0 charge. That is our zwitterion. D. D. All right, yeah. Getting a bit excited. 34. Diagram shows a gas chromatogram for a sample containing 4 isomers with the molecular formula I can't read because I ain't got my glasses on. What is that? C6H12O2, I think. The carrier gas is nitrogen and the stationary phase is polar. Which of the isomers is most abundant? You can see the one that is highest, that is the most abundant one. I'll circle it here. But it what was I going to say? It had the third longest retention time, but not the longest. Now, polar molecules are going to stick to the stationary phase, right? The carrier gas is nitrogen. Nitrogen's a covalent molecule, a non-polar molecule with no dipole. So the carrier gas, substances that are non-polar are going to have a very small retention time. So our far left peak is going to be non-polar. The others are going to be polar because they're taking longer through the system because they're attracted to the stationary phase. They have a high affinity for the stationary phase. R1 is kind of in between. It's not the most polar molecule. This would be the most polar molecule, the one on the little peak on the far right, because it's got the longest retention time, so it's more attracted to the stationary phase than it is the carrier, which is non-polar. And the most non-polar is the one on the far left, the second most abundant. So when we look at these, which ones of these are polar? Well, this is very polar. This is less polar. This is symmetrical, so is non-polar. I would say that's our far left one that had the shortest retention time because it's attracted to the nitrogen and didn't have a high affinity for the stationary phase. I would say D is our answer. That's the second most polar molecule. You can see it's not symmetrical. It's got the negative charge on that side, on one side. I would say the other one has got is even more negative, the one at the top there, A. So I'd say this D is our answer. It's the second most polar molecule in my opinion. There we go. Is that the end of the test? That was quite a difficult question. Is that the end of the test? Is that the end of the test? Oh, 35. One more. And this is the end of the test. Which structure is formed when phenylalanine is in solution at pH 3? Right, pH 3 is an acid, so loads of hydrogen ions knocking about. So instead of being NH2 on our amino group, it's going to be NH3 plus, and our carboxylate group is going to be COOH. Basically, you want to hydrogenate the molecule properly, right? And the only one that's hydrogenated, let's have a look. That's NH. That should be NH3 plus, so no. And again, this bit NH2 plus, no, that should be NH3 plus. It can accept another hydrogen, like in ammonia, you know, when it's got 4 bonds nitrogen and it gets the positive charge. So the only one that's correct is A because it's fully hydrogenated. Okay. Beautiful, wunderbar. Sharing's caring. Hit the like, punch up the bell, subscribe. I'll catch you later on the next video.
You're still here? It's over.